Assalamu alaikum. Welcome to the first lecture of chapter 3. The title you can see is Crystal Structure and Crystal Geometry. As we have discussed in the introduction chapter when we were introducing the whole course, there are two ways in which we can proceed with this basic course. Either we talk of crystal structure from the beginning, after introduction of course, which is the material science, that what is happening at the crystal level in metals. Or, as I sometimes do, we start with, in my scheme, what is chapter 6, mechanical properties of metals. So if I start with chapter 6, then I am starting with the application side first, so that as engineers, whatever, mechanical, civil, electrical, petroleum, industrial, as engineers, if you want to design a product, if you want to manufacture a product, then you need to know the materials, the properties of the materials. So therefore, okay, I am taking material science. My main purpose is to know about the properties so that I can select a good material for my product. So that is the application side, right? So if you start with the application side, then at the end of chapter 6, when you know the properties, tensile properties, hardness properties, impact properties, and so on, then the question arises, what is the reason that these materials have these properties? If we want to change the properties, how can we do that? What is the reason behind these properties? So if we want to change the properties and we understand the reasons, then we can go back and change them or improve it or produce materials with new properties, improved properties, and so on, right? So this chapter, crystal structure, is the reasoning behind the properties, that if steel has these type of properties, why is it so? If aluminum has these type of properties, why is it so? If a ceramic has these type of properties, what is the reason? Right? So this reasoning chapter can be, in one scheme, the starting point of material science after a general introduction. And in the other scheme, we can do material properties first and then come to this. Okay. Now, in the book that I was following is Smith and Hashimi. I have repeatedly told you that you can use Smith and Hashimi if it is available. You can use Callister if it is available. But just the headings of the chapters that I am using is from Smith and Hashimi. So chapter 2 in that book is atomic structure and bonding. In Callister also, or in any good materials book, the first chapter is always introduction. The second chapter is generally this atomic structure and bonding and so on, so that the basis for crystal structure and material properties and so on is there. You know what is atomic structure. But we know that you have covered it in Thanaviya, in a school. You have covered it in your initial years in the university, year 1, year 2, and so on, in chemistry and in physics. So here, as I say, it is a quick reading assignment because it belongs to basic chemistry and physics. And we will not ask any questions from chapter 2. But why am I asking you to quickly reread it? Because shells and orbits and atomic structure and so on do make a small basis of understanding. So now we start with the crystal structure thing. So if you read, then we are saying that physical structure of solids mainly depends on the arrangement of atoms, ions, or molecules. If the atoms or ions are arranged in a repetitive three-dimensional pattern, this is called long-range order. And if there is this repetitive long-range order, then this gives rise to what is known as crystal structure. The properties of solids depend upon the crystal structure and the bonding force. an imaginary network of lines with atoms at the intersection of these lines represent the arrangement of atoms in what is called a space lattice. We will show you in the figure. A unit cell is that block of atoms which repeats itself to form the space lattice. So there are hundreds and thousands of repetitions of what is the unit cell. Materials arranged in short range order, not long range, in short range order, do not have a crystal structure, and are called amorphous, without any geometric form or non-crystalline. Okay, so here we are describing materials which have a crystal structure, and therefore all those materials which do not have a crystal structure are called amorphous. Materials that have a crystal structure do possess a long range order, and materials that do not have a long range order is called short range order and amorphous or non-crystalline. So let us look at the figure. We are just trying to show you that a space lattice means there is some arrangement of the atoms, and these lines are imaginary lines, right? We are just that each one of them is an atom, or each one of them is a molecule sometimes, but each one of them is an atom, and therefore there is layer 1, layer 2, layer 3, right? If you go deep, then the top layer is the first layer, then the second layer, then the third layer. But in each one of them, if we can find that suppose there is a cubic structure which we have separated here, right? That there is a sort of a cube, or a cuboid. A cube would mean that all angles are 90 degrees and all sides are equal. But if we say it is a cuboid, then it can mean that all the three angles alpha, beta and gamma can be different, and all the three sides A, B and C can be different. So it is like a tilted cube or a cuboid, right? But the perfect shape will be that all three sides are equal and all three angles are 90, and then it is a perfect cube. So a space lattice means that there is a unit cell, it is a cube or like a cube, and this cube repeats itself hundreds and thousands and millions of times. So when it repeats itself a lot of times, then we call the whole thing as a space lattice, and the smallest identifiable geometrical shape in the space lattice is called a unit cell. Okay. Now the specific values of lengths and angles create different unit cells. Only 7 different types of unit cells are necessary to create all space lattices we will see in the table. And based on variations of these lattice systems, A. J. Bravais, 1811 to 1863, showed that 14 standard unit cells can describe all possible lattice networks. So we will see that. We will see first a table and then a figure. And out of these 14, there are 4 basic types called simple, body-centered cubic, face-centered cubic, and base-centered, right? So we will see. So this is the table that we were talking about. Classification of space lattices by crystal system. So crystal system, axial lengths and interaxial angles, and the space lattice name. So in cubic, there are 3 equal axes. A is B is C, right? A, B and C are equal. And all the 3 angles alpha, beta, gamma are 90 degrees. So this is basic cubic, isn't it? Basic cube means all the 3 angles are 90 degrees and all the 3 sides are equal in length. So this is cubic. In this cubic, there can be simple cubic, body-centered cubic and face-centered cubic. We will see, right? It is cubic, but simple, body-centered, face-centered. Then there is tetragonal. The 3 axes are at right angles So all the angles are 90 degrees. Any two of the sides are equal but not equal to the third side. So this is tetragonal. Orthorhombic, three unequal axes, A and B and C, none of them are equal. In tetragonal, two were equal, third was unequal in length. Here all three lengths are unequal, but the angles are still all 90 degrees. Right? So we will see on the next page, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic. These are the basic crystal systems in terms of the geometry. So let us see. Cubic, right? Cubic. All three sides are equal, all angles are 90 degrees. Simple cubic is this. Simple cubic. It is a cube and atoms are only on all the corners. All the corners. The top face 4 corners, the bottom face 4 corners. So total there are 8 atoms, right? And it is a simple cube. Body centered cubic. It is still exactly the same cube, but one extra atom is there exactly in the center. All other 8 are there, top 4, bottom 4 are there on the corners, and one in the center. Then we still have cubic. So this simple cube is there, but when we say face centered, then now on each face, top face, right face, front face, bottom face, left face, back face, on each face there is a center atom, right? In the top there is a face centered, on the right there is a face centered, on the bottom there is a face centered. So if there are 6 faces, isn't it, on any cube, front and back, left and right, top and bottom, there are 6 faces. So there will be 6 extra atoms now, if it is face centered. In a body centered, there is 1 extra atom exactly in the center of the body. But in a face centered, there is 1 extra atom on each face. So there are 6 extra atoms. So all these 3 are cubic. Simple cubic, body centered cubic, face centered cubic. Tetragonal is like this, that you start with a cube but elongate it, right? You start with a cube but elongate it. So the top and the bottom are very square, but the other sides are like rectangles, right? So if you see, 2 of the sides are equal, right? This side and this side are equal. A and A are equal, A and B. But C is unequal. C is unequal. So when we say A is equal to B, we say that A is equal to A in this, right? So again, in this, there could be simple tetragonal, body centered tetragonal. So cubic and tetragonal. Let's proceed. Orthorhombic. Orthorhombic, the 3 sides are unequal. A is different, B is different, C is different, but all the angles are 90 degrees. So this is orthorhombic. It again could be simple, base centered only in the top and bottom, face centered, body centered. And then you can go through these. Rhombohedral. All the 3 sides are equal, 2 of the angles are equal, 1 angle is unequal 90 degrees. So it is called rhombohedral. Hexagonal is very important. Hexagonal simply means there is a hexagon. So the top and the bottom are hexagon, where all sides are equal, A, and all angles in the hexagon are equal. And then there is one side height, the C, right? So alpha, beta, gamma are all 90 degrees, but it is hexagonal, simple hexagonal, and so on. Monoclinic, triclinic are like tetragonal, but at different angles and so on. So go through them. They are pretty simple. And here I am showing you all of them again, tetragonal, orthorhombic, hexagonal, and so on. So just so that you become stronger in it. So the previous slides and this slide, you just go through them a few more times. It has basically got nothing to do with material science as much as basic geometry, right? So just please revise them a few times so that you are very clear about the geometry.